The other algorithm that we'll look at for finding minimum spanning trees is Kruskal's algorithm, and it will help us to avoid some of the problems that we had in the performance of Prim's algorithm, but it will have some quirks of its own as well. We can create trees, in fact, multiple trees, out of each of the vertices, a singleton tree out of every single vertex, and say that vertex is its own tree. At the start, I don't assume that I know it's connected to anything. And remember that when we have multiple trees stored in a data structure, we sometimes refer to those as a forest of trees. We usually would do this with the disjoint set abstract data type that we talked about recently. We can then insert all of the edges from that tree into a minimum priority queue. And we'll repeat the following process until only one tree remains, meaning that there are no other trees in the forest. And just like for prims, we don't have to do anything fancy for detecting this. We can just keep a count of how many trees there are, and that will do the job just fine. So we loop on removing the least cost edge from the priority queue. This lets us get the best connection between pairs of things and rely on that we have that best connection later. So if the two end vertices from that edge are in different sets or different trees in our forest here, then they're not already connected yet. We haven't built them into our spanning tree. So we can add the edge to the set of edges that record our spanning tree, and we can do the union of the two sets, the two trees, in that disjoint set data type that have those two vertices in them. This is safe to do because we know that we haven't already drawn a connection between those two vertices. Remember, our minimum spanning trees need to be trees. They need to not have cycles in them. If we allowed adding edges to vertices that already were connected, meaning they already were in the same tree in our forest of trees, then that could create cycles. But we're able to make the connection because we know those two sets are disjoint, and we're able to rely on that connection because we know it was the minimum cost connection between those edges. So let's look at an example of this. We have a graph with only these 5 vertices in it and some values assigned for those. And we create a forest of all of the vertices in their own individual trees. We have the set of our edges, and down here I have them listed in priority from lowest cost or lowest weight to highest cost or highest weight. And we so far know nothing about the edges that will be in our minimum spanning tree. So we take a look at the lowest cost edge, AD. We see that A and D are in different trees right now. So we merge those trees and we add AD to the set of edges that represent our minimum spanning tree. Then CD is the next lowest cost edge. And we see that the tree containing C and the tree containing D are disjoint. They're not connected already. And so we merge them. We do the union of them. And we add the CD edge to our answer for our minimum spanning tree's edges. We do the same with DE, and that allows us to merge E's tree into this larger one. Now, what if we encounter an edge like AC, that A and C are already in the same tree? So we know there's already some connection between A and C. It's an indirect one here, but that we used minimum cost edges to build that already. So there's no need to worry about this AC edge. We already know that it has higher weight, higher cost than the edges that we've used so far, and we know that A and C are already connected in our minimum spanning tree. If we introduced the AC edge into our minimum spanning tree, it would no longer be a tree. It would have cycles in it. So we ignore AC. We don't even have to evaluate whether it's lower cost than what we've seen already because we know it is. We know we did lower costs in the minimum priority queue before we got to that edge. So the last edge we need is the BE edge to connect B into our minimum spanning tree, and now we have it. We have a full set of connections between every vertex in this graph here. We have a tree because it contains no cycles, and we know it's minimum because we selected the lowest weight, the lowest cost edges at every step. On a larger graph, this can look a little complicated. So we need to have all of the edges from that larger graph in priority order. You'll notice I couldn't fit them all into one column, so I have them going left to right, top to bottom, 1, 1, 2, 2, 2, 3, 3, 3, 4, etc. So we'll deal with them in that order because that's their priority. So we have that graph G. We establish our forest of singleton trees where we have no connections yet established between the vertices. And then we're going to examine the edges. We look at the lowest cost edge first. AD had cost 1, had weight 1. So A and D will get merged into a single tree, still a small tree, and everyone else is singletons. The edge CF is next, so we merge the C tree and the F tree, and we have another tree of 2, and everyone but them and AD are singletons still. CE allows us to grow that tree and connect to E, and then EG allows us to grow that tree even a little further and connect G in. HJ allows us to make a little tiny tree over here between just H and J, and we need that because that's the lowest cost edge connecting those two there. FG is not helpful to us. In fact, as I mentioned before, if we added it, we would have a cycle in this small tree here. But there's no need to go back and try to evaluate, oh, is this better than the connections I already have? Because I have been doing minimum weight connections at every step. So I already know that G is connected into this tree by an edge that's lower than the 3 of the FG edge. In fact, it's a value of 2. And I know that F is connected into this tree by a cost that's lower than that 3 of FG's edge as well. So I ignore it. It's not safe. It's also not helpful because it's higher cost, higher weight than the edges I've already used. So GI as an edge is helpful because I wasn't connected in already. And then we can connect J and I, and that builds our tree and merges it with this other small tree over here. DB lets us grow our smaller tree on the left and make it a little bigger. BA is another unhelpful edge, but it's higher cost than the connections to A and equal cost to the connection to B. So it's not helpful. It's not useful. It would be unsafe to add it. We ignore it. And then we see that B and C are not connected, but we have an edge between them that's the next lowest priority. And now all of our trees have been connected. We have no singletons left. We have no disjoint trees here. We have only one tree, and that tree is the minimum spanning tree. So we're done. We can quit early without evaluating those remaining edges there. Sometimes we're able to do that if we see that we only have one tree remaining. So Kruskal's algorithm has a running time of O of E log V, or number of edges times log number of vertices. It's logarithmic in the order of vertices because those trees will contain the vertices, and those trees do logarithmic lookup for them. When we have to see if 2 vertices are in the same tree or different trees, we'll do a log V lookup potentially of each of those. And we have to do those log V lookups for potentially every edge. We have to process every edge at least to insert them into the min heap, and sometimes we have to process the edges to do the lookups of the vertices that represent those edges. In the worst case, we may have to test every single edge. If the only edge that connects our last vertex that really needs connected into our tree is also the most costly edge. So if we had one edge that was cost 100, but it connected some vertex X that nobody else connected to, we would have to go through every edge with a lower cost than 100 before we hit that last one. So this E may be real. We may actually do log V type lookups for all E of the edges. That means that Kruskal's algorithm is best if the graph is sparse, if there are not many edges and things are not very interconnected in there. Then we can use this algorithm to process through the edges much more quickly and find our minimum spanning tree. So in summary, we had two algorithms for finding these minimum spanning trees, and minimum spanning trees can be a very helpful thing to have. They help to make some choices about how you want to connect between the different the different vertices in a graph, such as if you had deliveries all across a town, you could build a minimum spanning tree of the roads in that town because you need to be able to visit every one of the locations that you need to make a delivery to. So it includes all the vertices and some connection between all of those vertices. That's the lowest cost among all of those connections. So Prim's algorithm was good for dense graphs where they were highly interconnected, and Kruskal's algorithm was good for sparse graphs where they were a little less well connected, fewer edges between them. Both of them use priority queues, and Kruskal's algorithm used the extra data type of a disjoint set to build those trees. And remember that Prim's algorithm required updating the priorities inside of the priority queues, which is not the best efficiency operation for the standard priority queue. There are specialized priority queues that do this better, but typically updating priorities once you've got something in a priority queue is a little bit messy. But we have two different algorithms that can handle graphs and may perform better or worse in particular types of graphs to find these minimum spanning trees, to find this way that we can get access to all of the vertices with minimum weights, with minimum cost.